Assalamualaikum and good afternoon, everyone. Alright, so today we still discussing about chapter 2, total quality management, and we are going to discuss about statistical process control. Okay, so these are the learning objective. Okay, the first objective is to define the concept and application of SPC or statistical process control. Then construct a control chart for variable and attribute data. Okay, these are the content of this lesson. Statistical process control, then we are discussing about control chart, then development of control chart and control chart patterns. Okay, first one is statistical process control. Okay, we take periodic sample from the process and then plot sample points on control chart, determine if the process is within limit, prevent quality problems. Okay, so basically SPC is a method that we want to monitor a process. Okay, we want to monitor either the process is within the control or out of the control. Okay, for example, we have a machining process. Okay, we want to cut a sample into a round shape, and we have been set to cut into the diameter of, let's say, 5 centimeters. Then we will have some plus and minus. Okay, so let's say the plus and minus is 0.5 cm. Okay, so we want to make sure that every single workpiece that we cut are within the limit. So we have the upper control limit, lower control limit and upper control limit, and this axis is the axis of the sample, or the sample in the time unit. Okay, for example, we take first sample on first hour, second hour, third hour, and so on. Okay, so from there, basically from the control chart here, basically we can observe or we can monitor either the process is within the control or out of the control. Okay, alright, so about the statistical process control and variation. Right. Okay, so variation is basically a common causes. Variation inherent in a process can be eliminated only through improvement in the system. Okay, variation mean there is a slightly differences in our process. Okay, for example, in machining process, in cutting process, right, maybe the variation here is the vibration of the tool that we use, or maybe the method of operator doing the job. Okay, maybe during the morning shift they are still in a good focus, but later on for the afternoon shift they already having a less focus. So means that this reason or these causes will contribute to the variation in the process. Okay, it can be eliminated only through improvement in the system. So we must conduct the continuous improvement for the system. Then special causes of variation. Okay, variation due to identifiable factor, right, can be modified through operator or management action. So this one is related with the factor that we can identify. All right, so for this one is quite straightforward, where we can focus to solve this problem directly. Okay, then we move to the type of data. Alright, so we have the attribute data. which is a product characteristic evaluated with discrete choices. Okay, it can be measured like good, bad, or yes or no, right? So this is the attribute data. Then another one is variable data, which product characteristic that can be measured, okay, such as length, size, weight, height, time, and velocity. So attribute data is like just the answer is yes or no, or accepted, accept or reject. Okay, 1 or 0. So these are the attribute type of data, while the variable data means that the data that we measured, for example the length, the diameter of the machine part that I give an example earlier, might be the diameter is 5.2 cm or maybe 4.9 cm. The other example is the weight, maybe the weight is 52.4 kg, okay, 64.5 kg, and so on. So means that these are the variable data and these are the attribute data. Okay, so the control chart is a graph establishing a process control limit. Okay, control chart. Okay, for a control chart we have a different type of control chart for different type of data. Okay, for variable data, okay, we have or we use mean or known also as X bar chart and R chart. Okay, while for attribute data we use P and C chart. Okay, so we will learn how to construct this chart later on. Right, so the in general, this is the process control chart. Okay, so basically for the control chart we have this feature on this side, okay, the sample number, right, or it can be also translated into the time that we measure. Okay, then here is the lower control limit or LCL, and upper control limit UCL, and process average or the mean readings. Okay, so once we obtain the related point, so we will plot the point and we just make a line to construct the line here, and then from there we need to observe either the point that we taken is within the control or out of the control. Okay, so as an example here, one point is given that out of the control because it's above the upper control limit. A process is in control if, okay, number of sample point outside the limit, okay, no sample point outside the limit, so means that all the points are within the range. Okay, so when all the points are within the range, we can say that the process is in control. Okay, the second criteria is most point is located near the process average. Okay, then number 3, about equal number of point above and below center line, then points appear randomly distributed. Okay, so in order to identify or summarize either the process is within the control or out of the control, we need to assess these 4 criteria. Okay, in terms of number of sample, no samples outside the limit, okay, point is located near the average, okay, let's say this is the average, and we have the point mostly near the average. Okay, then about equal number of point above, okay, number of point above the center line and below are roughly the same, and point appear randomly distributed, so there is no pattern that we can observe that means that it didn't in the random distribution. So means that the point must be in random distribution. Okay, development of control chart. So now we are going to discuss how to construct the control chart, okay, based on in control data. If non-random causes present, discard the data and correct control chart limit. So we need to consider this criteria. So we must collect the data in control data. Based on in control data means that we know that in control data means that the data that we collected during the machine is in the normal operation. So if we know that if the process is not behave normally, so we cannot collect the data during that time. Okay. If non-random causes present, discard the data. So if we know that non-random causes appear, so we need to remove the data from our consideration. Non-random causes means we know the reason for the different variation. Maybe for example, if the machine using the compressed air, for example, we know that we have a problem with our compressor and we collect the data during that time. So that one is invalid data. So we must collect the data during the normal operation. Then correct control chart limit. So we need to identify what are the numbers or value for upper control limit and also lower control limit. Okay, next is about control chart for attributes. Okay, for attribute data, okay, we use P chart and C chart. Okay, so again for attribute data, the data is like yes or no, 1 or 0, accept or reject. Okay, this type of data. So we use P chart. Okay, so P chart calculate percent defective in sample. Okay, it calculate the percentage of defect. Okay, then C chart is a count number of defect. Okay, C chart is based on the count numbers. Okay, then this P chart is based on percentage. Right. Then control chart for variables. Okay, we also have two control chart for variable data. Okay, the first one is mean chart. This one is basically better known as X bar chart. Okay, it use average of sample, control the central tendency of the process. Okay, X bar chart means that we plot the chart based on the mean value. Okay, then range chart is the R chart, or sorry, range chart also known as R chart, use amount of dispersion in the sample. So this one is based on the range. So for example, if we for one particular sample we take 5 reading, for example, so the first reading is let's say 0.25, the second reading is 0.72, the third reading is 0.26, then 0.41, 0.31. Okay, so based on this data, okay, the range is between 0.25 to the maximum is 0.72. Okay, so we take the difference here. Okay, this is for the range chart. X bar chart is directly calculated the average. So we sum up all of these numbers and we divide with number of that data here, which is 5. Then we will get the X bar. Right. Okay, now we want to learn about the chart limit. Okay, how we can calculate or define the limit, the upper control limit and lower control limit for the chart. Okay, so we begin with X bar chart. Okay, for X bar chart, when we know the sigma, this one, okay, the sigma here is representing the standard deviation. Okay, this one. Okay, so upper control limit is x double bar plus z time with sigma x bar. Okay, lower control limit x double bar minus z time x bar, sigma bar. Okay, x double bar is the mean of sample mean. Okay, so x bar is the mean, x double bar is the mean of mean. Okay, so in our chart later on, we will get a few numbers of x bar. Okay, then x double bar is the when we calculate the mean for this data. Okay, z is the number of normal standard deviation. So this one is normally we are setting it as a fixed value. So later on I will explain. Standard deviation of the sample mean, okay, is given in this form. Then population standard deviation, S is the number of population, N is the sample size. Okay, so the sigma there represent the sample standard deviation. Okay, so how to calculate standard deviation? Right, so the standard deviation is the square root of number of samples here. Okay, so we'll put it in detail later on. Okay, for example here, okay, for example here, okay, I have okay, I want to monitor the weight of oat flakes. Okay, so I want to calculate, or I want to monitor for 12 hours. Okay, hour 1 to hour 12, and for each hour here, okay, for hour 1, this is the data that has been collected. Okay, for hour 1, okay, we collect 9 samples. Okay, so the first sample is 17, second is 13, then third is 16, and so on. Okay, then from here basically we can calculate the mean. Okay, so the mean of the first hour sample is being putting here. Okay, right, then for the second hours, okay, again we collect 9 sample data. Okay, some sort of like this one. Okay, then we calculate the mean for the second hour is 16.8. Okay, so they repeat this process until the 12 hours. Okay, and from there basically we can calculate the upper control limit and lower control limit. So in this case the standard deviation is given as 1. Okay, all right, so now we can calculate the upper control limit. So upper control limit is x double bar. So x double bar is the mean of the mean. So mean, we add all of this value. Okay, we sum up of this value, and then we divide with number of hours here, 12. Okay, so for when calculating x double bar here, so this value is 16. Okay, then plus with z is equal to 3. This one is given. Okay, basically we can refer to the standard table that normally will be given. Okay, then the value on this side, okay, which is sigma x bar, is sigma square root of n. Okay, sigma is 1. Okay, sigma x bar equal to sigma time with divide with square root of n. Okay, so sigma is 1 and n is 9, so this one is n. Okay, don't get confused. N, okay, the number of sample here with the number of reading that we made. Okay, sometimes students are getting confused between this number and the number of observation that we made. Okay, n is referring to 9. Okay, alright, so from there we can calculate upper control limit. Okay, 16 plus 3 times 1 per 3, so 17 ounce, and lower control limit is 15 ounce. Okay, so now we want to plot the chart. Okay, so we have the number of sample, number of observation. Okay, 12 observation because we have 12 hours here. Okay, sometimes it's called sample number. Okay, so from the calculation we know that the lower control limit is 15, upper control limit is 16, and the mean is upper control limit is 17, the mean is 16. Alright, so now we want to plot the data. So for the first hour, okay, the mean is 16.1. So we put in this graph 16.1 here. Then for the second hour, 16.8. Then we plot 16.8. Then we do for the rest of the data. Okay. Alright, so variable due to assignable cost, variation due to assignable cost. So basically from this chart we find out that there are 3 points that out of the limit. Okay, indirectly, okay, we can conclude or we can say that the process is out of the control. Remember the 4 criteria that we need to observe to conclude either the process is within the limit or not. Number 1 is no point out of limit. Okay, so here we already find out that there are 3 points out of the limit. Okay, and then criteria number 2, point near to mean. Okay, the points are near to the mean line. Number 3, number of point above and below roughly equal. Okay, so from here also we find out that the number of point above here 1 2 3 4 5 6 7 8 compare with 1 2 3 4. Okay, the number of the point is already not balanced. Okay, balance here doesn't mean that it must be equal. Okay, but if like this, half of the point 4 of the point out of 12 is below. Okay, so it shows some variation, and number 4 is the no random pattern. We have the random pattern. Okay, so next is for X bar chart when we don't know the sigma. Okay, previously in this example the sigma or standard deviation has been given, okay, but in the case that we don't know the sigma or standard deviation, okay, this is the formula: upper control limit x double bar plus a2 r bar, lower control limit x double bar minus a2 r bar. Okay, R is the average range of the sample. Okay, A2 is control chart factor found in the table, so we need to refer to the given table later on. Okay, so this is the standard table that we need to refer, okay, when calculating the upper control limit and lower control limit. So we need to refer based on the number of sample size n. Okay, and again, do not confuse the number of sample size with the number of observation that we made. So in the previous example, the number of sample is 9, right? Okay, so suppose we use this value for A2. Okay, this is another example, the different example. Okay, process average x double bar is equal to 12 ounces. Okay, average range r bar is equal to 0.25, the sample size n equal to 5. So in this example, this number are directly being given, but normally in the question, this information is not being given. You will be supplied with the table, the detail of the table, as in okay, as in the example here. Okay. Alright, so means that you need to know how to calculate x double bar, how to calculate r bar, and how to determine n, number of samples. So for upper control limit x double bar, okay, 12 plus with r bar is 0.25, r bar is 0.25, but A2, so we need to refer to the table with n equal to 5. So for A2 value, when n equal to 5 is 0.577. Okay, so from there we can calculate upper control limit. Okay, we also can calculate the lower control limit. Okay, this one is for R chart. Right, so from there we can plot the graph. Okay, upper control limit, lower control limit, and also mean. Mean is the process average, x double bar is here. Okay, now for this example, okay, observation, okay, slip ring cm, slip ring diameter in cm, okay, observation. Alright, so now we need to plot the x bar and r chart. Okay, so normally in a question, you will not be it will not mention that you need to plot either r bar or x bar chart or r chart, because both of the chart must be draw together. You cannot just draw one chart. Okay, and you need to understand what type of chart need to be drawn based on the given data. So based on this data, we know that these are the variable data. So for variable data, definitely we need to use x double bar and r chart. Okay, right. So the first thing, okay, careful with the number of samples. Okay, number of sample reflected the number of data used to calculate x bar. Alright, so now if we have this data, I believe that some student will define the number of sample is equal to 10, okay, because we have 10 samples here, okay, but actually the number of sample is referring to this one, okay, equal to 5, because okay, number of sample reflected the number of data used to calculate x bar. So in order to calculate x bar, we take this number and divide with 5. So means that the number of sample is 5, not 10. So 10 is the observation, the number of observation that being made. Okay. Alright. Then the second thing is, okay, before that, you need to understand how to calculate R here. Okay, R is the range of this data. Okay, range means equal to maximum minus minimum data. Okay, so the maximum is in this first set here is 5.02 and minimum is 4.94. okay, so if we minus these two, 5.02 minus 4.94, so you will get the range 0.08. okay, again for the sixth observation here, the maximum reading is 5.06, the minimum reading is 4.96. okay, so if we minus these two, so we will get the range of 0.1. and for x bar, I believe you understand how to calculate it. Okay, alright, so now we want to calculate the limit, upper control limit. Okay, so the formula is x double bar plus a2 r bar. Okay, okay, x double bar is we take this summation, okay, 50.09 divide with number of observation 10. So this is x double bar. So you will get 5.009. Okay. Then A2, okay, refer to the table, earlier table with n equal to 5, and R bar, okay, this one is obtained from the mean here. So we calculate the summation of R and we calculate the mean. So R bar is a mean for R, which is 1.15 divide with 10. Okay, so we can calculate the upper control limit. Okay, then next restaurant control limit. Okay, this is for the different problem. Okay, then if we can calculate UCL, we also can calculate lower control limit, x double bar minus A2 times R bar. Okay, restaurant control limit. Okay, this is for a different problem. Okay, for salmon fillet at Darden restaurant, okay, we have the x bar chart and R chart. Okay, so I repeat again. Okay, this is for the previous calculation is for x bar chart. Okay, so we already finished for R bar chart. So to summarize the previous one, okay, for x bar chart, so we have two ways how to calculate the upper control limit and lower control limit. Okay, for the problem with known standard deviation or sigma, okay, we use this formula. okay, for the problem that we know the value of sigma, standard deviation. Okay, then for the problem with unknown sigma, okay, we use this formula to calculate the control limit. Okay, alright, so now we move to R chart. Okay, roughly for R chart, is a type of variable control chart. Okay, again, R chart will be used together with X bar chart. Okay, it cannot be used alone. X bar chart also must be used together with R chart. Okay, show sample range over time. So we want to observe the range of the data. Okay, difference between smallest and largest value in the sample. I already explained how to calculate the range earlier. And monitor process variability independent from process mean. So means that this R chart, okay, don't have any relation, do not have any relation with X bar chart. Okay, but we need to use these two charts together. Alright, so again for R chart we need to calculate the upper control limit and lower control limit. Okay, so for UCL, the formula is here, D4R bar. For lower control limit, D3R bar. Okay, so R bar you already understand is the average of the sample, and D3 and D4 are control chart factors from the table. If you remember the previous table that where we find the value of A2, okay, we use the same table to determine the value for D3 and D4. Okay, so average range, okay, this is an example. Okay, for average range 5.3 pound, okay, sample size equal to 5. Then from table D4 2.115, D3 equal to 0. Right, so if we look back at this table, okay, for the sample n equal to 5, so D4 is 2.115 and D3 is 0. Okay, so basically this table will be attached together in your question, so you can refer to it. Okay, right, so from there basically we can directly calculate limit for upper control limit for R chart and also lower control limit for R chart. Okay, so the mean is the R here, the R bar value. Then upper control limit is from the calculation, and lower control limit is also from the calculation. Okay, again the similar example. Okay, I already explained how to calculate the range here. Then we got the summation of the range, and then we can calculate average of the range, or R bar. Okay, so from there basically you can plot the graph. Okay, we can plot the graph of this value. So means that for when we are doing the plot, okay, I just put here. Okay, we have upper control limit, lower control limit, then we have the mean R bar. Okay, then we have 10 period here. Okay, so the first value here is referred to this one, 0.08. Okay, so based on the calculated upper control limit and lower control limit, so you need to put where is the first data is located, then the second data, okay, for example like this. Okay, I don't know, and then later on you just connect this line, okay, to get the data. Okay, this slide showing the mean and range chart. Okay, why we need to use both chart together. Okay, for the first one, sampling distribution result in the chart below, and sampling mean is shifting upward but range is consistent. So if we use the X bar chart here, okay, we can see that the mean detect the shift of central tendencies. We can observe that the value of the mean for the process is shifted, okay. But if we just use our chart, for example, we cannot detect the changes in terms of the central tendency. So if we look at the range, so it is quite good, quite stable at the central range point, okay. So means that if we just use one chart, our chart, we cannot detect the shift or the changes in the central tendency, okay. So if we look at the range of the chart here, okay, between this one and this one, okay, the range is roughly the same. So that's why it is not being triggered under the R chart, okay. And the same things also goes, okay, if we just use X bar chart, okay. So based on X bar chart in this example, we can see that the mean of the value is quite consistent, located at the central line, okay. X bar chart does not detect the increase in the dispersion or in the range, but when we use R chart, we find out that the range or dispersion is changing, okay, from below here going slightly up and then going to the out of the control, okay. Then if we look at this graph, okay, the central or the mean of the chart is roughly consistent, but the range here, it was changing, okay. So it also shows that there is something wrong with the process, okay. The range of the minimum and maximum has changed. For example, if this is the data during the day 1, for example, day 1, day 2, day 3 and day 4, okay. For example, for the day 1, the range is quite good and the means is also located at the correct place. On the second day, the mean is still at the required position, but the range is slightly dispersed. When we compare to day 4, the range is slightly the range is very dispersed, but the mean is still at this position. So it shows that our plus and minus value is already shifted from data of day 1 until day 4, okay. So in this case, we also need to investigate why the range of the data has a dispersion, okay. So we need to use X bar and R chart together. So each measure the process differently. So X bar measure the central tendency, while the R chart measure the dispersion, okay. Both process average and variability must be in control, okay. If any of the point in these two charts are out of the control, we need to investigate further the reason for it, okay. So we are finished on X bar and R chart. So now we move to the next type, okay, control chart, okay. Before that, this is the general guideline how to create a control chart. Take a sample from population, compute appropriate sample statistic, okay. Use sample statistic to calculate control limit. So we need to calculate the control limit and then plot sample, investigate possible assignable causes, then continue sampling. So this monitoring process must be made continuously. Alright, so next we move to attributes control chart. Okay, control chart for data for attributes. Okay, so for the attribute, we can we already defined that this is the type of data. Okay, good, bad, yes, no, acceptable or unacceptable. Okay, so measurement is typically counting defective. Okay, so basically we count the number of defect. Okay, chart may measure percent of defective, P chart, or number of defects, C chart. So again, we can for attributes type, okay, we can use these two chart. Okay, we begin with P chart. Okay, population will be binomial distribution, but applying the central limit theorem allow us to assume a normal distribution for the sample statistics. So this is the formula for control limit of P chart. Okay, upper control limit P bar. Okay, P is a mean fraction defective in the sample. Okay, so we calculate the fraction or percentage of the defect from the sample. Okay, this is the mean. Then Z is a number of standard deviation. So SP, standard deviation of sampling distribution, and N is the sample size. Okay, so for standard deviation, so we can calculate the standard deviation using this formula. Okay, so P square root of P bar times 1 minus P bar divided with N, number of sample. Then for Z values, okay, in this one we have the Z values. So for Z values, smaller Z values make the graph more sensitive. Okay, makes the charts become more sensitive. Okay, this is the standard value that normally we use for Z. Z is equal to 3.0. So otherwise it being stated in other form, so we will use this value. Means that if the question didn't mention other value for Z, you need to use Z equal to 3.0. Compromise between sensitivity and error for this value of Z. Okay, this is an example. Sample of work of 20 clerks. Each clerk entered 100 record. Okay, number of sample, we have 10 sample here. 20 sample of the clerk, means that 20, you can define it as 20 clerks or 20 different time job that be conducted while in different time. Okay, alright, so we have the sample number, we have the number of error or number of rejected or defect, then fraction defect. So how it's calculate the fraction defect here is equivalent to number of error divide with total total count, which is 100 here. Okay, so 5 divided with 100, 0 divided with 100, and so on. Okay, from there you can calculate the fraction defective here. Okay, so in the end we can calculate the P bar. So this is the P value. Number of error here represent the P value. Sorry, the P value is fraction defect here, P. Okay, so from there you can calculate the P bar. Okay, P bar is total of error, which is 80, divide with 100 record multiply with 20 clerks. Okay, so you will get 0.04. right. Beside that, okay, beside using this one, you also can calculate the P bar, okay, by sum up the fraction defect here. So you will get the summation of fraction defect, then divide with number of sample 20. So we will get the same number. Okay, Then for standard deviation is p bar, okay, as mentioned in earlier slide, equation to equal to p bar times 1 minus p bar divide with number of sample n. Okay. Alright, so from there we can calculate the upper control limit and lower control limit. Okay, so UCL is p bar, Z, okay, p bar is 0.04, Z is 3.0, the standard deviation is 0.02, so you get this number. Okay, then for lower control limit, 0.04 minus 3 times 0.06 is equal to 0. Okay, if you calculate this one carefully, 0.04 minus 3 times 0.02, you will get minus 0.02. Okay, but why here it stated LCL equal to 0, not 0.02. Okay, this is because the type of data that we use here is the defect data, okay, fraction of the defective, and there is no such minus defect. Okay, so for example, we have 100 samples. Okay, there is no minus value for the defect. Okay, it is not possible to have that one. Okay, the number of defect must be larger than or equal to 0, larger or equal to 0. It cannot be negative value, it cannot be less than 0. This is it cannot be like that. Okay, that's why for lower control limit, okay, once you calculate and get a negative value, so you need to put this value as 0. Okay, please remember that. Okay, so from there you can plot the graph or the chart as usual. Okay, so we have upper control limit here, lower control limit, and also p bar value. Okay, then this value is taken from the fraction. Okay, so for the first sample here, okay, the fraction is 0.06, the second one is 0.05, so we transfer that value into this chart. Okay, 0.06, 0.05, okay, 0, and so on. Okay, so from there basically we can observe, okay, based on the 4 criteria that I mentioned earlier. Is there any point out of the control? Yes, we have one point out of the control. Is it the number of is it the point is roughly located near the central line? Yeah, most of the point are located near the central line. The number of point is roughly the same above the central line and below the central line, so yes, roughly the same. Is it any pattern, specific pattern, and so on. So basically from the first criteria we find out that there is one point that out of control, so we have possible assignable causes present. So means that if we want to improve this one, we need to investigate further why this is happened. Okay. Then the second exercise or second example here, 20 samples of 100 pairs of genes. Okay, roughly the similar example as the first one. So we calculate the number of error, then the fraction defective. Again, the fraction here is equivalent to number of error divide with the number of samples, 100. Okay, next we look at the control limit for C chart. So previously is P chart. P is stand for percentage. So now we move to C chart. C is representing the count. Okay, so this control chart is constructed based on the number of defect count. Okay, population will be Poisson distribution, but applying the central limit theorem allow us to assume a normal distribution for the sample statistics. So again, these are the formula for upper control limit and lower control limit. Okay, C bar is the mean of the count. Okay, then multiply with 3 and square root of C bar. Okay, so this is an example. So we have the number of complaints over 9 days period. So we have number of complaints 3, 0, 8, 9, 6 and so on for 9 days period. Okay, C bar equal to 54. So if we add the total here is 54, then divide with 9, so you will get C bar. Okay, so on average there are 6 complaints per day. So first of all, we can differentiate right now. This is based on number of complaints, so we cannot calculate the percentage here, because 3 here is referring to the number of complaints, and we actually don't know how many we don't have basically the number of total samples here. So 3 is just 3, we cannot divide 3 with 100 and so on, because this one is not available. So for this type is referring to the P chart. Okay, so this one right now we are constructing the graph solely based on the number of defect that we have. Okay, so C bar complaints per 9 days. Okay, UCL C bar plus 3 square root of C bar, so we get 13.35. Okay, then for lower control limit, C bar minus 3 square root of C bars, we get the 0. And again here, if you calculate this value, you will get negative something. Okay, negative value. So once you get negative value, so we put as a 0. Okay, again, because we don't have negative complaint. Okay, we don't have negative complaint. Okay, then from here basically we can plot the graph. Okay, so the central line here is referring to this value 6, then upper control limit and lower control limit, and then put the value inside the graph. Okay, the first maybe the first day here is 3. Okay, number of the complaint for the first day is 3, then 0, then 8, 9, 6, 7 and so on. Okay, so basically based on this graph, okay, there is no point that out of the limit, all the points are within the limit. Then we also need to assess other criteria to conclude either this process or this activities is within the control or out of the control. Okay, this is for exercise. Okay, the number of defect in 15 room. So we have 15 samples. Okay, so means that for this one, you first you need to decide which type of chart to be used, P chart or C chart. But based on the data here, okay, there is no information about the total samples or everything, so means that we cannot calculate the percentage. Okay, so means that this is for C type data or C chart. Okay, so again you need to calculate the number of defect 190, and you calculate the C bar, divide with 15, so you get the value, and from there you can calculate UCL, LCL. okay, C bar plus 3 square root of C bar. Okay, right. So now which control chart to use? Okay, variable data, definitely you need to use X bar chart and R chart. Okay, observation are variable. Okay, collect 20 to 25 sample of n equal to 4 or n equal to 5 or more each from a stable process, and compute the mean of X bar chart and R chart. Then track the sample of n observation. So attribute data, you can use P chart. Okay, observation are attribute that can be categorized as good or bad. We deal with fraction, proportion or percent of defect. Okay, there are several samples with many observation in each. So it means that when we know the fraction or proportion or the percentage, we can use P chart. Then for C chart, okay, when we deal with the number counted, which is small part of a possible occurrences. Okay, defect may be number of blemishes on desk, complaint in the day, crime in the year, broken seat of the stadium, and so on. Okay, so means that we didn't have information about the fraction, we just know the number of defects, so we use C chart. Okay, next is a pattern in a control chart. Okay, so normal behavior process in control chart. So this one I already mentioned, there are 4 items need to be assessed. Okay, is it any points out, or any of the points here is out of the control? Is it the number of points above and below are roughly the same? Is it the point are located near to the central, majority of the point are located near to the central point, and there is no obvious pattern of the graph. Then pattern in control chart. Okay, the first one here is one plot is above, out above or below, investigate for cause, process is out of the control. So this one is because of 1 point out of the range. Okay, trend in either direction. So for this type, all of the points are within the control limit, but there is a obvious pattern. Okay, trend in either direction, so it has a trend. Okay, increasing trend or decreasing trend. Okay, okay, then run 5 above or below central line. So means that for this one, the points, majority of the point are above the central line. Okay, so this one also need to investigate for the reason or for the cause. Okay, then erratic behavior, investigate. Erratic behavior means the point are having a sudden jump. Okay, from here suddenly to this point, from here suddenly going down. Okay, this one also can be related with the indicator, while most of the point, majority of the point should located near the central line or targeted line. Okay, so this one is also need for investigation. Okay, next is about sample size determination. How we can how we need to set, or how we can determine the number of sample to be observed, okay, in order to construct control chart. Okay, attribute control chart, 50 to 100 part in sample. Okay, so this one is attribute. If we want to plot P or C chart, okay, so these are the number of sample, 50 to 100 part in a samples. So for variable control chart, okay, there's 2 to 10 part in a sample. For one sample mean for one reading. Okay, if you have the control chart here, okay, number 1, 2, 3, 4. Okay, let's say the first point here. Okay, this is the one sample. This is one sample, one sample. Okay, let's say we collect 5 data for the first sample. Okay, so means that it's within the range. Okay, let's say 5 data here, 5 data for the second sample, 5 data for the third sample, and so on. So the range for each sample is like this one, 2 to 10. So that's all for this lesson. Okay, thank you.